I will give you a presentation entitled Automatic Extraction of Amendments from Polish Statutory Law, which was a collaborative work between me, Mateusz Piech, Zbigniew Kaleta, and Krzysztof Wróbel. Three of us work at the AGH University of Science and Technology, and Krzysztof
This meeting is being recorded.
Works at the Jagiellonian University. So the agenda is really quick. I will start with the amendment in Polish law, then the annotation procedure, the approach we apply to extracting these amendments, the experiments, and I will reach the conclusion. So to give you some context, we are working on a LEMKIN, an intelligent legal information system, which will provide question answering in the domain of Polish statutory law. And so we have to access the most recent regulations because the law in Poland changes very often. So, and the other problem is that the consolidated texts are published, but only once or twice a year. And the laws are distributed only as PDF. So we can look at these documents as semi-structured data. So to give you some numbers, for instance, in 2019, there were 20,000 pages of new laws enacted in Poland. So this is a very large number. So I think that doing that manually, processing these amendments manually is not an option. So we have developed this amendments pipeline, which includes four stages. Amendment span detection. Then when we detect the spans, we interpret these spans. Then we also have to detect the spans related to the dates when is the application of given amendment, and then we have to interpret these dates. So this presentation concentrates only on the third step, so the amendment span detection. Here you have an example of an amendment definition in the bill. Blah blah blah. The following amendments are introduced. For instance, in Article 20, paragraph 2b, in the introduction to the enumeration, the words paragraph 2 are replaced by paragraph 2a. Okay, these are the amendments we have in Poland. So, and you can see that we have some specific items here or entities. For instance, the location of the amendment, the identification of the old content of the provision, the new content of the provision, as well as the type of amendment. So let's now move to the annotation procedure. And let's start with the annotation types. So we have identified three groups of spans. The first group is amendment type. We have content addition, content removal, content change, as well as unit addition, unit removal, and unit change. The difference here is that in the first case, the content is changed. The content inside the provision is changed. In the other three types of amendments, we have the full unit. The full unit is changed in some way. And also we have change ID, which is not, I don't think it's very common in literature. So this is something which is, let's say, discovered. The second group of annotations are identifiers. We have a new ID, amended ID, and preceding ID. Usually, the most important thing is the amended ID. But if you provide a new unit, you have to identify the preceding ID. And also, we have the last group is the content. And you have, as you have seen, for instance, we have the old content and the new content. Also, in some cases, there's the preceding content. So these are the types of annotation we have identified. And regarding the data set which was annotated, there were more than 240 bills of Polish statutory law from the years 1998-2018. This data set was split into train, development, and test sets in proportion 80-10-10. And the documents were not divided. We kept the documents in a specific part of the data set. And the statistics are as follows. We have more than 400,000 tokens. More than 200,000 tokens didn't receive any annotations because we thought that it is not necessary to annotate them. On the other hand, almost half of the remaining tokens received some kind of annotation. And when we look at the amendment types, roughly we have identified roughly 5,000 amendments in this bit, which I think is quite a large number. Okay, so let's move to the approaches we have applied to this problem. So the first thing we did with the documents were pre-processing. Because we wanted to apply the family of BERT models, we have to somehow fix the problem of the 512 subtoken limit. So first of all, we try to just use the documents as they are and use only the 500 tokens which are at the beginning of the document. But it turned out that such an approach, first of all, gives very low coverage. It only covered like 40% of the documents. And the other problem was that the numbers were very low, especially the micro F1 measure was quite low. So the second approach, we split the sentences using a library devoted to Slavic languages. So it gave us 100% coverage. And in these preliminary experiments, we observed 94% macro F1 and 84% micro F1, which was still too low for our expectations. So we have devised more sophisticated pre-processing. We split by sentence, but not inside a span. If the sentence was split inside one span, it was not this span was not divided, but this procedure could be only applied to the training data. So during inference, we split by the smallest part of a provision. The provisions are structured so, and you can identify the lowest level of this provision. So during inference, we apply the model to this smallest part of a provision. So the models we have used, first of all, we used a very simple approach based on regular expressions. So this is the rule-based approach. Then we used the family of BERT-based models, Roberta, which is the English Roberta, XLMR, which is a multilingual BERT, and Herbert is a Polish version of Roberta, so to say. And as a last model, we used by RNN, so recurrent neural network. Actually, we used the FLAIR library. So regarding the rules, what we can say about the you can see all the rules we have applied, which are very short, and we think this is the biggest advantage of this approach. But the problem is that we couldn't identify a rule for the preceding content tag. As well, we have like a large number of false positive, especially related to the IDs, because the IDs can be part of the amendment definition, but these IDs can be also in the content of the amendment. So this approach is not very general. Then the BiRNN model, it was based on the character level language model. So the model was trained to predict the next character in the text, and it was combined with the token level language sequence labeling model. So this is the approach used in FLAIR, and we provided two versions of this, one trained on the sentence split, and the second trained on the optimized segmentation. And the last one, the last family of models were, as I said, was BERT, Roberta, XLMR, and Herbert. I won't get into the transformer architecture because I think that there was so much time already spent discussing BERT. So I will move to the next slide. So the experiments. These are the results of our experiments. the best results were obtained using the BiRNN approach. But let's first look at the rules. As you can see, the micro, macro, and weighted F1 scores are pretty low for this approach. So this justifies our machine learning approach. Then, when you look at the BERT-based models, we can see that the Roberta model, which was developed for English, not for Polish, gave the best results, which is a kind of a surprise. And the last observation is the fact that the BiRNN model gave the best results, which are almost perfect in this setting. So to explain the probable reason for that is no hyperparameter optimization for the BERT models. And we know that the hyperparameters are usually crucial for obtaining very good results. But we thought that it's not, because the results were so high for the BiRNN model, and all of these experiments were run with the default parameters, we thought that it's not necessary to try to find the best hyperparameter combination. So to conclude the presentation, the recurrent neural network turned out to be the best. The neural network models work better than the handcrafted rules, which is kind of obvious. But what is crucial here is the pre-processing. As you have seen, if not some special pre-processing was applied to the documents, the results would be much worse. And what was not presented is the part related to the interpretation of these spans, but we have already implemented such an algorithm, which is very simple, and it produces very good definitions of the amendments, which can be applied directly to the text. And my general idea, which might be a bit controversial, is that to make the neural network model do the smallest task, which is hard to code, and then let the algorithm do the rest. This is like an opposition of this end-to-end approach. I think that it's much easier than to interpret the processing of the whole solution than in the case when you try to learn the model end-to-end. So thank you for your attention, and I'm waiting for the questions.
Thank you, Mr. Aleksander. I have one question for you.
Yes.
At the end of the paper, you say that a problem related to the topic of the paper is the detection and processing of temporal expressions that determine the date of application of a certain additive. How do you think this issue could be solved?
Okay, so I put this can be resolved in two stages. The first stage is detection of the spans, as you can see here, right? So this spans, this structure of the definition of the application date is it is well structured. It is well structured, not very well structured, but it's quite well structured. But then you have to apply some interpretation algorithm. So for now, I don't have a direct resolution for that, but for sure, I would apply some kind of temporal logic model, temporal logic inference engine to resolve this problem. I don't think that using neural networks for that makes sense.